Hello and welcome to our video lab report. My name is Leong and joining me today are my group members Aanisah and Hazirah. We are presenting experiment E1 for the course SSCP 2811. The title of our experiment is half-wave and full-wave rectifier. In this video, we will explain the setup, show our result, and discuss what we learned from the experiment. Let's begin.
Before we dive deeper into this experiment, let me share the objectives of this experiment first. The objectives of this experiment are to record and compare the input and the output waveforms of a half-wave rectifier, to record and compare the input and the output waveforms of a full-wave rectifier, and lastly to record and compare the input and the output waveforms of the rectifier with a capacitive filter. This experiment was done using a transformer 12V, oscilloscope, digital multimeter, project board and connectors, 2 units of diode 1N4007, resistor 10 kΩ 0.5W, capacitors 22 microfarad, 100 microfarad and 50 microfarad and a red LED.
And now we will move on to the theory of half-wave and full-wave rectifier. A rectifier is an electronic circuit that converts AC into DC. AC voltage constantly changes direction. Most electronic devices need DC, which flow in only one direction. Rectifier use diode because a diode allows current to flow in one direction while blocking the other. Half-wave rectifier. A half-wave rectifier uses only one diode. When the AC input becomes positive, the diode contact and allow the positive half circle to pass through. When the AC signal becomes negative, the diode blocks it completely. As a result, only half of the AC waveform appears at the output. This creates a DC signal with large gap between each pulse. The output is not smooth, has low average voltage, and is not very efficient. However, it is simple and cheap to build. Full-wave rectifier. A full-wave rectifier improves the output by converting both the positive and negative half circle of AC input into positive voltage. This can be done either with 2 diodes or with a bridge rectifier using 4 diodes. Because both halves of the AC waveform are used, the output is more continuous. The frequency of the pulse doubles and the gap becomes much smaller. This produces a smoother DC signal with higher average voltage and better efficiency. Overall, a full-wave rectifier is stronger, smoother, and more efficient compared to a half-wave rectifier. It delivers a better DC output with fewer gaps, making it suitable for most power supply applications. Half-wave rectifiers are mainly used for simple, low-power circuits.
For the procedure of this experiment, we carried out 2 main parts, the half-wave rectifier and the full-wave rectifier. Each main part involved a wave rectifier with a capacitive filter and with capacitive filter. I will begin with the half-wave rectifier setup. First, we prepare the circuit as shown in here and install channel 1 at point A and point C, and channel 2 at point B and point C. Channel 1 was set as AC mode and VRMS was obtained from this channel. Channel 2 was in DC mode and VRMS level output was obtained from channel 2. For the half-wave rectifier with capacitive filter, a 22 microfarad was added as shown here. Channel 2 was set as DC mode and VRMS level output was measured. Channel 2 was then changed to AC mode. The Y scale was adjusted until the ripple graph covered half of the screen display and peak-to-peak voltage VPP of the ripple was measured. The steps were repeated by using the capacitive filter of 100 microfarad and 50 microfarad. Next, we move on to the full-wave rectifier. The steps were quite similar to the first part and the circuit was constructed as here. Note that there are 2 diodes involved in this part. Channel 1 at point A and C was set in AC mode and channel 2 at point B and C was set in DC mode. VRMS level output was obtained from channel 2. After that, we move on to the full-wave rectifier with capacitive filter. From the same circuit, add a 22 microfarad as shown here. Channel 2 was set as DC mode and VRMS was obtained from this channel. Channel 2 was then changed to AC mode. The Y scale was adjusted until the ripple graph covered half of the oscilloscope display and VPP was measured. The steps were repeated using capacitive filter 100 microfarad and 50 microfarad. Before ending the experiment, we switched off all the equipment and disconnected the components safely. These steps completed the procedure for both the half-wave and full-wave rectifier experiments.
This is the result for experiment E1 half-wave and full-wave rectifier. Part 1. We measure the VRMS with the uncertainty 0.01 volt. For channel 1, we get 12.58 volt. For channel 2, we get 8.39 volt. Part 2. We measure with the different capacitor. For the 22 microfarad capacitor, we get the VRMS is 16.23 volt and the peak-to-peak voltage is 168. For the 100 microfarad, we get the VRMS is 47.32 and the peak-to-peak voltage is 352. For the 50 microfarad, we get the VRMS is 16.92 and the peak-to-peak voltage is 712. Part 3, we measure the VRMS. Channel 1 we get 12.82 and channel 2 we get 12.34. For part 4, we measure again with different capacitor. For the 22 microfarad, we get the VRMS is 70.19 and the peak-to-peak voltage is 860. For the 100 microfarad, we get the VRMS is 70.44 and the peak-to-peak voltage is 208. For the 50 microfarad, we get the VRMS is 70.34 and the peak-to-peak voltage is 380.
Discussion. Rectification is the essential process of converting alternating current AC into direct current DC, enabling standard household power to be compatible with modern electronic devices. This conversion relies on diodes, which act as one-way electrical valves due to their symmetrical properties. Rectifiers are primarily classified into two types, which is half-wave rectifiers and full-wave rectifiers. Half-wave rectifiers utilize a single diode to only allow the positive half cycle of the AC signal to pass, resulting in a pulsating output with significant gaps where the negative cycle is blocked. Full-wave rectifiers provide a more efficient output by utilizing both halves of the AC cycle. This experiment specifically employs a center-tap full-wave rectifier, which uses a specialized transformer and two diodes to ensure current flows through the load in a single direction during both the positive and the negative cycles. While the rectifiers successfully convert AC to pulsating DC, the resulting output is often too bumpy for sensitive electronic components. To address this, a capacitive filter is connected in parallel with a load resistor. A capacitor acts as a temporary energy storage device. Its operations can be divided into two distinct phases, charging phase and discharging phase. Charging phase is when the rectified voltage rises toward its peak. It exceeds the voltage stored in the capacitor. The diode conducts and the capacitor quickly charges up to the peak value of the AC signal. Discharging phase is when the AC cycle drops toward the zero. The diode becomes reverse biased and stops conducting. During this gap, the capacitor takes over and begins to discharge its stored energy into the load resistor. The primary goal of this capacitor filter is to prevent the output voltage from dropping to zero between pulses. This results in a smoother DC signal with a smaller ripple voltage. The effectiveness of this smoothing depends directly on the capacitance value. A larger capacitor can store more charge and discharge more slowly, leading to a much flatter and more stable DC output. The experiment consists of four main parts, including half-wave rectifier in part 1, half-wave rectifier with capacitive filter for part 2, full-wave rectifier in part 3, and lastly, full-wave rectifier with a capacitive filter in part 4. Each part consists of one LED in a circuit to compare each brightness, with the objectives to compare all input and output waveform obtained. In part 1, where a half-wave rectifier is conducted, an AC supply is connected in series with a diode and a load resistor, which is LED in this experiment. This operation can be broken down into two phases. In the positive half cycles, the diode is forward biased, acting as a closed switch or short circuit. Current flows through the load, producing an output that follows the input signal, such that in figure part 1 shows, the output waveform or the yellow wave consists of humps representing only the positive cycle of the input, which perfectly tracks the blue wave, which is the input waveform. However, the output peak-to-peak voltage is approximately 18.4 volts, which is slightly lower than the input peak-to-peak voltage of 36.8 volts, mostly due to the diode's internal voltage drop, which is typically 0.7 volts for silicon. In negative half cycle, the diode is reverse biased, acting as an open switch. This blocks all current flows, effectively clipping the negative portions of the waveform to 0 volts. This configuration is highly inefficient, as half of the available power from the AC source is wasted. This creates a larger gap in power delivery, where the load receives no energy for 50% of the time. In part 2, where a filtered half-wave rectifier is tested, a capacitor is placed in parallel with the load to bridge the gap between AC pulses. The diode conducts and charges the capacitor during the positive half cycle, while during the negative half cycle, the diode shuts off and the capacitor discharges through the load to maintain the output voltage. Experimental result shows that increasing the capacitance significantly improves the DC quality. For example, in capacitor of 22 microfarad, providing a minimal smoothing with a large ripple voltage of 1.68 volts due to the rapid discharge, because the half-wave rectifier only provides one charge pulse per cycle, the capacitor must support the load for a long duration. Theoretically, the capacitor runs out of steam or discharges significantly before the next positive half cycle arrives to refill it. Second, for 50 microfarad, we observe that the ripple peak-to-peak voltage drops to 712 microvolts. By more than doubling the capacitance, the ripple is cut by more than half. The downward slope of the sawtooth wave in the figure is less steep, indicating a slower discharge rate, which is matched in the theories. The larger the storage capacity, using the formula of Q equal to CV, maintains a more stable voltage during the off period of the diode, resulting in a higher average DC level. Lastly, for 100 microfarad, the ripple peak-to-peak voltage is at its lowest for this set, which is 352 millivoltage. This provides the best smoothing for a half-wave circuit, thus maintaining the voltage near the peak with the smallest ripple. This improvement is governed by the time constant tau equal to RC. A larger capacitor increases tau, causing the stored energy to release more slowly. This effectively fills in the gaps between the pulses, reducing ripples and creating a steadier DC signal. Next, in part 3, a center-tap full-wave rectifier uses a specialized transformer to split the AC signal into two halves, allowing two diodes to work in tandem. As expected, the voltage measurement peak-to-peak shows 18 volts for output. This is roughly half of the total input of 37.6 volts, because the center-tap divides the secondary voltage in half. It is observed that in the first positive half cycle, a positive pulse output signal is produced, meaning that the diode 1 is forward biased and conducts while the diode 2 is off. While in the negative half cycle, the input has been inverted into positive pulse output waveform. This is because the role reverse, D2 conducts while D1 is off. Unlike the half-wave rectifier, which wasted half of the input, this dual diode action, where D1, diode 1 and D2, diode 2, take turns conducting, ensuring the current flows through the load during the entire cycle, which produces 2 pulses per cycle as a continuous and reliable DC output. As a result, this gives a continuous power, as there are no longer any dead times or dead zones or flat lines at 0 volts, because the load receives power during both halves of the AC cycle. This full-wave unfiltered provides an advantage in terms of higher efficiency, as it is twice as efficient as half-wave rectifier, because it utilises the full AC signal and produces higher output. It delivers double the average DC voltage and power to the connected device. In this part 4, the circuit is rectifying both the positive and negative halves of the AC cycle. The output waveform changed from bumpy pulses of the unfiltered rectifier to a much smoother, nearly flat line. Because full-wave rectifier, for every one complete cycle of the blue sine wave, there are 2 peaks in the yellow ripple waveform, which produce 2 pulses per cycle. The gaps that the capacitor needs to fill are significantly smaller than in the half-wave version. The result shows when the capacitor is increased from 22 microfarad to 100 microfarad, the following was observed. First, 22 microfarad, we can observe that the voltage peak-to-peak ripple measures around 860 millivoltage, millivolts, showing that this is the largest ripple among 3 tests because 22 microfarad capacitor is relatively small storage tank. The capacitor loses voltage quickly during the discharge phase. A smaller capacitance value results in shorter time constant tau, leading to a more pronounced sawtooth shape and higher ripple voltage, but already much smaller than the half-wave counterpart. The capacitor discharged slightly between peaks, but the next peak arrived quickly to recharge it. Second, for 50 microfarad, the voltage peak to peak ripple drops significantly to 380 millivolts. This is because by more than doubling the capacitance, you have roughly half the ripple. The sawtooth peaks are much closer to the top, and showing that the capacitor is better at holding its charge between the rectified pulses. Means as the capacitor increases, the discharge rate slows down, providing a more stable DC level. Lastly, for 100 microfarad, figure part 4 shows that the lowest peak-to-peak ripple voltage of 208 millivolts, it is observed that the capacitor charged rapidly, which we can see that the steep upward slope, and this discharge slowly, which we can saw that the longer the downward slope is. The shallow discharge slope of the sawtooth waveform demonstrates the high time constant tau provided by the 100 microfarad capacitor, resulting in a highly stable DC output. In this experiment, the LED brightness serves as a visual indicator of the average DC voltage being delivered by each configuration. The half-wave unfiltered rectifier produced the dimmest light due to significant dead time between pulses, whereas the full-wave configuration appears brighter as it is utilized both halves of the AC cycle to double the energy delivery. When capacitors were added, the LED reached its maximum steady brightness in the full-wave circuit because higher ripple frequency recharged the capacitor twice as often, maintaining a stable voltage near the peak. Lastly, this experiment successfully demonstrates that full-wave rectification combined with high capacitance values providing the most stable DC output by minimizing ripple voltage. To ensure safety and accuracy through the process, it was vital to verify all circuit connections and maintain correct polarity for diodes and electrolytic capacitors before applying power. Furthermore, selecting capacitors with voltage ratings exceeding the circuit's peak voltage and using proper oscilloscope grounding were essential precautions to prevent component failure and electric shock. Finally, turning off the power supply when swapping components or adjusting the breadboard serve to protect both the user and the sensitive electronic equipment from the damage.
Firstly, as we can see from the results shown earlier, the frequency of output and input for both half-wave rectifiers and full-wave rectifiers are the same. The half-wave rectifier has a frequency of 49.98725 Hz, and the full-wave rectifier has a frequency of 50.02569 Hz. After doing some calculations, the time constants in part 2 and 4 are 0.22 second for 22 microfarad, 0.5 second for 50 microfarad, and 1 second for 100 microfarad. A larger capacitor increases time constant, causing the stored energy to release more slowly. Here, the full-wave rectifier gives a higher DC voltage. That's because it uses both halves of the AC input, so more of the energy actually reaches the load. Meanwhile, half-wave rectifier only uses one half, so the average DC output is lower, just like we can see from this formula. As we can see, the brightness of LED in part 1 is dimmer than in part 3, because in part 1, that is the half-wave rectifier, the LED only lights up on one half of each cycle, so it is dimmer and less power to make the LED brighter. By doing this experiment, we can understand better that rectifiers are literally everywhere, like in televisions, computers, chargers for mobile phones. Other than that, it is also important to filter the DC output from rectifier circuits, because the raw output voltage still contains ripple, and many electronic components, especially digital circuits, require a steady and stable DC supply for them to work properly. Filtering will smoothen out the voltage and prevent damage to sensitive components. And that's all for the questions. Those are basically the main things we can conclude from the rectifier experiment.
Conclusion. In this experiment, the input and output waveform of half-wave and full-wave rectifier were successfully observed and compared by using the oscilloscope. The full-wave rectifier is more efficient and producing a higher DC output voltage. The additional of capacitor improved the output by increasing the DC voltage and reducing the ripple. The 100 microfarad capacitor were most effective with 17.44 voltage in part 4 compared to 22 microfarad and 50 microfarad capacitor. This proves that The larger capacitance provides a smoother and more stable DC output.
And that brings us to the end of our presentation. We hope we all take away something valuable in understanding half-wave and full-wave rectifiers. Thank you for watching.